Okay, so let's talk about the final really quick. Are we early? Let's see, what time is it? A couple minutes early. Anybody have any questions to ask me about anything? Any questions? Yes.
I was not here on Tuesday, and so I'm going back. While you were solving the waveform equation, at one point you wrote minus omega t and it by plus. Does that not matter? It be plus omega t, like kx plus versus.
I'd have to go over the specific spot in the derivation. So it might just be a sign error or something. So, any questions about anything before I go and ask about? But I'll take a look at that. Yes. Okay, so the final is going to be about 70% new material. So we're going to spend a lot of time in this week and next going over the final part of optics, not optics, but the light chapter, and we're going to go over the relativity chapter. Everything that you're expected to know in terms of what could be on the exam regarding the homework is posted. You've got the assignment on special relativity. That's it. There's not going to be any more homework assignments. The chapters that we were going to do, we're not going to do any more chapters. That would be too much material for this course to be a fair course, in my opinion. So I've cut 3 chapters out of the recommended material, but it's all geometrical optics. So even though it's a lot of rules and a lot of miscellaneous tidbits about light, but it doesn't really tell us anything about the underlying physics as much. So it's not as important. And we went into circuits in depth because circuits are very important for general understanding of electronics. They play a big role in our lives. So it made more sense to do circuits in depth because of the percentage of people here who are going into engineering. But optics is a very fascinating topic. It's not that it isn't fascinating. So I wish we could add another quarter to the physics curriculum, and then we could do that course and some other ones that you probably skipped over, or they covered it, but they covered it so fast you didn't really get to learn it. Okay, so to recap, 70% of the final is going to be new material. 30% is going to be material that we've covered before that's cumulative. However, I'm not going to put any material on there that you haven't seen in some form on the homeworks or the exams, and I'll try to give a sort of targeted selection of topics. In other words, I don't think it's fair for you to spend very much time studying for the cumulative material. I understand that the relativity material is dense and challenging. I want you to mostly focus on the relativity from here on out, and the optics, the light stuff that we're going to do today and the other lectures before. So this chapter and the next chapter that I have the homework assigned, focus most of your time on that. How about this? No circuits on the final. That'll be a great way to save some time. No circuits, no phasor diagrams on the final. What are we going to put on the final? That's cumulative. Let's do magnetism. That's fair game. Let's say up to Faraday's law. And then, of course, magnetic fields that you could find, magnetic torque, that sort of thing. Well, magnetic dipole, I should say. Very, very targeted list. No circuits, no phasor diagrams, none of that stuff. That way you can really focus your time on studying the new material. I think that's a fair, everybody agree? That's fair? Okay, good. I think we got a fair arrangement here then. Okay, so any more questions about the class or the final before I jump into the material for today? Yes. Yes, there's no new homework material. Everything that you need to know is on the table. We've got what? Just a little bit, about 2 weeks until our final. Is that right? So that's about right. That's about right. We've got 2 weeks to go. I think this is the good stopping point. I haven't covered all that material for relativity yet, obviously. It's going to take another week to cover all that material. Okay. Any more questions? Yes. Yeah, let's see here. Let's see, one more maybe. Yeah, we want this off. That's off. Okay. Is that okay, or do we need more lights off? Okay. I think there might be some controls for other lights. I'm not sure what these all do. I could just start messing with stuff. I don't think that has to do with... I'm not sure what all these controls are down here. This has to do with other stuff. Okay. I think that's good for now. Yeah, any more questions about what we're going to put on the final versus what I went over? Okay, great. So, electromagnetic waves carry energy. And I notice, I appreciate that everybody's coming to class. If you've got questions or you want to talk with people, try to keep the discussions minimized, because it's hard for everybody else to focus and pay attention when people are talking. So like continual talking is kind of a bit of a distraction. So that's my recommendation. You can talk during office hours. You can ask questions then. This is the time for me to present the material for everybody, and we've got to do it in a very precise manner. So try to keep the talking down to a minimum just during lecture. Okay, great. So electromagnetic waves carry energy. The energy in sunlight is an example. We've got microwaves, radio transmitters, and lasers. They all make use of wave energy. So how do we describe this energy? We can start with energy density, this concept that there's an energy per unit volume. So we look and we can see that in a region of empty space where there's electric and magnetic fields, the total energy density is given by this expression. We've got the expression for the electric fields. The energy density is, for the electric fields, 1/2 permittivity of free space, and then just the field squared, plus 1/2, and then mu goes in the denominator, B field squared. So we've got our energy density based off of the electric and magnetic field magnitudes. And then for electromagnetic waves in a vacuum, E and B are related by this expression which we found in the last class. So B magnitude is equal to electric field magnitude divided by C. Because remember, this is the same thing as 1/C. We found that from the wave equation last time. So we can also express energy density in a simple electromagnetic wave in a vacuum as this expression here. So we can do it just in terms of the electric field magnitude, and then it's it's twice this expression here. So this is just in terms of the electric field. So this shows that in a vacuum, the energy density associated with the electric field is equal to the energy density of the magnetic field. In general, the electric field magnitude is a function of position and time, and just like we had the sinusoidal wave described by that. So we're going to be describing things in terms of sinusoidal waves, cosine omega t plus some phase. And then we can get a lot done doing that, describing how the electric and magnetic fields oscillate as a function of position and time. Electromagnetic waves such as those we've described, they're traveling waves that transport energy from one region of space to another, transporting energy from here to there. We can describe this energy transfer in terms of energy transferred per unit time per unit cross-sectional area, or power per unit area for an area perpendicular to the direction of the wave travel. So let's draw this out on the board to see what I'm talking about here. So let's see. I want to actually make this bigger. So we've got this plane here. Draw our axes here. Okay. So we've got our travel. Let's put some different colors here. Okay. So we've got this. This is c dt. So we're looking at this speed of light traveling in a certain time, dt. That gives us units of what? Speed of light, a velocity times a time gives us units of what? Distance. So this makes sense. So we've got units of distance here. And then we've got another plane that this goes into. Erase this here so we can see this a little better. Okay. So we've got CDT here, and then we've got our vector, this new vector coming out of this surface. It's coming out of the area, and we call this a pointing vector. And we use the symbol S to describe it. Just like we had our area vector, dA, that came out perpendicular to the surface, we've got our pointing vector that comes out perpendicular to this surface as well. It's S. And then we've got electric and magnetic fields that are mutually perpendicular to this pointing vector. So guess what there's going to be associated with this pointing vector? What kind of mathematical, from vector calculus, structure do you think we're going to use to describe this pointing vector? What kind of product do we know gives us three mutually perpendicular vectors? And what product? Yes. Cross product. So let's see how that works. So we expect to see a cross product between E and B here that will describe this pointing vector. Okay. So we go back here. So to see how the energy flow, this pointing vector flow, is related to the fields, consider a stationary plane here, drawn here on the board as well. And we've got, let's see. And it's perpendicular to the x-axis and coincides with a wavefront at a certain time. So at a certain time here, there's a wavefront that's associated with this plane. And then at a different time, this wavefront is going to be moved on to a different point at the speed of light. So in time dt, the wavefront moves distance dx equals c dt to the right of the plane. Consider an area A on the stationary plane. So we've got an area A on this plane. The energy in the space to the right of this area had to pass through the area to reach the new location. So the volume dV of the relevant region is the base area, A, times the length, c dt. So we have volume, V, is equal to area times c dt. So the volume of this space that this box makes, it makes a volume here. And that's what we have described here. Okay, so we've got our volume, and then the volume of the relevant region is the base area times the length cdt, and the energy du in this region is the energy density times this volume. So our energy is going to be, energy density is going to be what? It's going to be energy per unit volume. So energy density is energy per unit volume. We have our volume here. What do we use to describe our energy? We just use U. So we have U dV. But then we know what U is in terms of this. It's given there. So we have E naught E squared times AC dt. Now, why are we leaving out the B field? We're not worrying about the B field right now because we also have an expression where it's just this, where we're not worried about the B field. So they're choosing to describe it just in terms of the E field at this point. It doesn't say that in the book, but that's what they're doing. That's a sleight of hand that they use there, because that could be confusing if you're wondering why didn't they include the B field there. Because they didn't have to for this energy density. We can just describe the energy density purely in terms of the E field using that equation. Okay, so we have du equals u dv, and now we have that expression. So it's epsilon naught E squared times A C dt. Okay. So then what's the next step here? So then we can figure out what this is, what this pointing vector, based off of this, we can figure out what S is. And actually, I don't like how they jumped to places here. So let's see a little bit. Let's go back just a tiny bit. Okay, so we've got this epsilon naught E squared times AC dt. Okay, that's good. We can see where they got that from. But then we can actually find that S is then proportional to this. So what they've basically done here is they've taken this and they've said this and this is equal to this root mu naught E naught over mu naught. So this becomes down here, and then we've got E squared still left over. So we have this constant here coming out, and then we can take this expression and we can equate it to that. Okay. So then we notice that because this had to go this way and it had to travel in a direction perpendicular forward, it had to basically it had to travel in a direction perpendicular to the plane. And why is that? Why do we know that this had to travel in a direction perpendicular to the plane? Because of Maxwell's equations. The only way that the light can travel is restricted by it satisfying Maxwell's equations. The only way it can satisfy Maxwell's equations is if it propagates in a transverse direction. So we know that this magnitude of this energy density, it has to have a direction associated with it, and that direction has to be going out of the board in this case from the way we've drawn it. So we know that the way to describe that is through the cross product. So the units of S are energy per unit time per unit area, or power per unit area. The SI unit of time of S is 1 joule per second meter squared, or 1 watt per meter squared. So we have power per unit area. That's the units that we're talking about to describe this physical process here. And we can define this quantity that describes both this magnitude that we've come up with here and this direction by using vector calculus, and we get our pointing vector. So the pointing vector then has to be E cross B along with our 1 over mu naught. So we go back to this expression here, and we relate this to this, and now we use our B explanation as well to get our description of the pointing vector itself. So S then is equal to 1 over mu naught E cross B. And there we go. So given our E field and B field, we can always calculate the direction and magnitude of our pointing vector. So that's what we're going to use whenever we have that kind of a problem. And the vector S points in the direction of propagation of the wave. Since E and B are perpendicular, the magnitude of S is EB over mu naught. So essentially, we take this expression and then we divide out by a certain amount to get the energy, and then we relate it to S, and then what the magnitude of S then is just EB over mu naught. So magnitude S is just EB. Magnitudes of both of these, I'll just leave them without arrows to denote that it's the magnitude we're talking about then, divided by mu naught. Okay, so this is the energy flow per unit area and per unit time. So the power per unit area through a cross-sectional area perpendicular, this cross-sectional area here, perpendicular to the propagation direction. So the total energy flow per unit time is going to be this integral. The power out of any closed surface is the integral of S over the surface. So we have this, we enclose this in some surface, some generalized surface, and then we have the total power is then the surface integral of the pointing vector over my dA. So we define a dA here, and so if my area vector is perpendicular to this plane, then S and dA are what? What are S and dA if it's perpendicular here? They're parallel. So then the dot product gives us a contribution, and this pointing vector has a value, and thus we have a power associated. But we have no power associated with other directions. This is limited to this point. So that's an important thing. The area vector defines where the power that we're getting is receiving. So why is this important? Let's say that we have a large enough sample of photons that we can treat this as a classical field, like a satellite. It's getting a broadcast. That's why the direction that the satellite dish is pointed in matters, because the power, the information of light that the satellite is getting has to be such that we're actually receiving the signal. So it matters which direction things are oriented for whether or not we receive the light. There's another example. These solar panels, they're tilted to be face on to the sun so that the pointing vector of the electromagnetic waves from the sun can be absorbed for the maximum amount. There's an angle there where they get the maximum amount of energy, because the sun basically the sun has some angle in the sky where the light is coming down and striking it directly at this angle. So for sinusoidal waves, the electric and magnetic fields at any point vary with time. So the Poynting vector at any point is also a function of time. Because the frequencies of typical electromagnetic waves are very high, the time variation of the Poynting vector is so rapid that it's most appropriate to look at its average value. The magnitude of the average value of S at a point is called the intensity of the radiation. So we can figure out what the intensity is by doing some substitution. So I've got my expression for for my Poynting vector. It's E cross B. But then I have my equations that describe what E is. So what is E and what is B? That tells me what the Poynting vector is. As a function of position and time then, it's going to be 1 over mu naught. And then what I'm going to do is I'm going to take brackets and I'm going to put everything else inside these brackets because I want to describe this wave in terms of a vector. So my E field is in the y direction. If I call this my y hat or my k hat or j hat direction, I should say. So they're calling this j hat. Sometimes we do this as k hat. And this, with it written this way, this is j. And then this would be k. So this is flipped a little bit from how we normally do it. Normally we tilt it like this. You could just think of it as this whole coordinate axis is rotated. Then this has to be I hat here. Or maybe minus I hat. Does that make sense, what I did here? Okay. So we've got our coordinate axes here. And then, yeah. Okay, so then if this is j hat, I have the amplitude is the maximum of my electromagnetic field. So how did they get this? First they assigned a vector to it, and then they said it's oscillating. So it has some maximum amplitude, and then it's going to be kx minus omega t. Where does this come from? It comes from this, cosine. So we have some E max value. This is the amplitude. And then it goes into negative minus E max. And then it has some period and some frequency associated with it. And this is like a phase offset. So this is the oscillation frequency where omega is equal to 2 pi f. So essentially what we're saying is, we're saying if this wave is sinusoidal, it obeys simple harmonic motion. We can use the same mathematical equations from simple harmonic motion to describe this E field oscillation in time and space. And then what we do is, that's the E component. Now we take the cross product. So I just did this, and now I'm translating it into this B field. And then it's got a k hat direction. So actually, I'll just put it around. Let's see. So I'm actually going to do double brackets. I'm going to do some big brackets here for the whole thing. And then I'm going to put this in these brackets, and then my B field in these brackets. And then I've got some maximum value of my B field amplitude, and it's also going to have a period and a phase associated with it, kx minus omega t. And it's oscillating in phase, so there we go. And then all of that has 1 over mu naught multiplied by it. So that's how I describe my Poynting vector in terms of the cross product. So when we take the vector products of j cross k, we get I hat, and cosine squared of kx minus omega t is never negative. So the Poynting vector always points in the positive x direction, like we've seen here. And the direction, it's the direction of wave propagation. And the x component of the Poynting vector then is given by this, E max times B max over mu naught, and then we've got this value here, cosine squared kx minus omega t. So what I had here is the description of my magnitude of my pointing vector. That's the maximum value that my pointing vector takes. But as you can see here, there's also this oscillation in time and space, kx minus omega t. So that's going to affect this value. This value is always changing with respect to time because of this oscillation function. And so this comes from taking the cross product. J cross K gives me an I hat, and then E max and B max multiply, because we'd put all these components in the, you know what I'm saying? We'd put like, okay, J, so we'd have 0, and then we'd have E max kx minus omega t, and then 0, and then for cross it'd be 0, 0, and then B max kx minus omega t. Okay, so then you just take the cross product of these three. So we have these three components here. These are different columns, obviously. And then you take that, and then you get this result. That comes from taking the cross product. We've done that a lot, so I don't think I need to show that. Does everybody see how I got that, though, from the cross product? Okay, great. So with that, we have our expression. And then the time average value of this cosine 2 of kx minus omega t is 0, because at any point, it's positive during one half cycle and negative during the other half, which makes sense because we've got an oscillation going on here. So we're going into positive during this half, negative during this half. So the average value of the pointing vector over a full cycle is just S average, where S average is E max B max over 2 mu naught. So we take this expression and we say that if this is the magnitude, then the average, we could use a little, they use a subscript, so we'll just do S average. It's just EB over 2 mu naught. And these are not equal to each other. These are two different things, so I'll do that. Two different things. Okay. So then we can see where all of this comes from. We've got that the magnitude of the average value of S for a sinusoidal wave is 1/2 the maximum value. And we can see these other relationships here as well. So here we have an expression for the intensity of the wave as well, not just the pointing vector, but also the intensity. So the intensity is equal to S average by definition. And then that's E max B max over 2 mu naught. And it's also given by these other expressions for it. So for a wave traveling in the minus x direction, the pointing vector is in the minus x direction at every point, but its magnitude is the same for a wave traveling in the positive x direction. Throughout the discussion, we've only thought about waves traveling through a vacuum. If it travels through dielectrics, these values of permeativity and permeability are replaced by the dielectric values. What's interesting is that the energy densities in the E and B fields, it turns out that they balance out and they respond to the dielectrics in such a way that the energy does not change. So that's an interesting thing. So the E and B field magnitudes adjust to the dielectric. And so the energy densities, whether it's in a vacuum or a dielectric, doesn't change. That's pretty interesting. At any point, the magnitude of the pointing vector varies with time, so the instantaneous rate at which electromagnetic energy in a sinusoidal plane wave arrives at a surface is not constant. This might contradict your normal experience. You might think that the light from the sun or a light bulb or laser is steady, but these sources do vary with time, but the variation isn't noticeable because the oscillation frequency is so high. So it's oscillating so quickly that it looks like it's constant. It'd basically be like if you were in a room and you were flipping the light switch on and off so quickly that your eyes couldn't detect the change. That's the same idea here of what they're saying. So what we do sense is the average rate at which the energy reaches our eye. And actually, what they said there isn't even completely true. It's more like it comes in bits. Each photon itself has a certain quantized value of energy, but there's just trillions of them, so it looks like blocks that come in waves. We don't worry about the photon part, though. We just focus on the wave-like part. So for the sinusoidal wave that we described before, assume that we have the electric field magnitude of being 100. Find the value of B, the energy density, and the rate of energy flow per unit area, S. So if I give you the electric field magnitude, I can give you that little piece of information, and you can find everything else from it, from those equations that we have now. So the E and B are going to be uniform behind the wavefront and 0 ahead of it. So the target variables of B, U, and S must also be uniform behind the wavefront. So given the magnitude of E, we can use our other equations to find B, right? Because if we know magnitude of E, we can find the magnitude of B from that, any one of these, honestly. And then to find U, we can use this equation, and then we can use that to find S. So let's see how we do this. So we're given B from this. So B is just the magnitude of the E field divided by C. So there we have our B value in terms of Teslas. And then U is just epsilon naught times E squared, which we know both of those. So now we have U. So now what's the magnitude of the pointing vector? It's just EB divided by mu naught. So you can see how cool this is. Using Maxwell's equations, we turned a very complicated geometrical problem of figuring out what light is doing in space, and we were able to turn it into a simple, like, algebraic relation where we can easily learn everything we need to know at all about the light from that. So this is a very easy problem that would be extremely difficult if we didn't have Maxwell's equations. Okay, so since E and B have the same values at all points behind the wavefront, U and S also have the same value everywhere behind the wavefront. And the wavefront, E equals 0 and B equals 0. In the front, before we get to this point, it's 0. That's what they're saying. It doesn't have a value until it's reached that point in space. That plane keeps traveling outwards at c dt. Okay. So now we have our value for our pointing vector. Now let's do another example with a pointing vector. Say a radio station on Earth's surface emits a sinusoidal wave with total average power of 50 kilowatts. Assuming that the transmitter radiates equally in all directions above the ground, which is unlikely in real situations, but we'll just assume that for this problem. It's a good enough back-of-the-envelope calculation, which is all you really do in practice anyway. Anyway, we do this and use this to find the electric field and magnetic field amplitudes, Emax and Bmax, detected by a satellite 100 kilometers from the antenna. So how do we figure this out? So we've got this satellite that's beaming this signal, and we've got this transmitter. So all the radiated power passes through this surface here. So the average power per unit area is the intensity, and the area here is not the area of a square like it was in this drawing here, because as this light travels out a certain distance, it travels out in all directions, and we actually have a signal that is more described by a sphere. And then it's the area through the sphere. So all the radiated power passes through this surface, so the average power per unit area is the intensity. So the area is 2 pi r squared, and the power was given to us, it's 5 times 10 to the 4 watts. So then we have the intensity from that. So intensity is power per unit area. Remember that. So then we have the intensity, so we have S average. And we use this expression for S average. And then, we have this expression for S average. We plug that in there, and then we use E max squared, take the square root of that to solve for E max. So now we have our value of E max from that. Does everybody see how we did that here? So we had the intensity. We had to solve for that. We had the power given to us. We know what the area is because we know the distance it is away. So we use pi r squared. And we get that. Remember, let's reread the problem. So it says that the transmitter radiates equally in all directions above the ground, which is why we have the situation. And then we have to find it detected 100 kilometers from the antenna. So our R is 100 kilometers. Does that make sense geometrically, what they're saying here for this problem? Okay, good. So then we now have E max from that expression. And then B max is easy. You just divide by the speed of light, and you get B max. So E max is comparable to fields commonly seen in a lab, but B max is extremely small in comparison to B fields. For this reason, most detectors of electromagnetic radiation respond to the effect of the electric field, not the magnetic field. So loop radio antennas are an exception where they do respond to the magnetic field component. So the electric field component is vastly larger than the magnetic field component, even though they both carry the same amount of energy in the same form, in a different way, actually different form. One's E fields, one's B fields. They carry the same amount of energy, but the magnitudes are vastly different because of the speed of light. However, when you get at higher velocities, this ratio starts to flip, and the magnetic field component starts to be more important for charged particles moving at high velocities and things like that. Okay, now let's talk about radiation pressure. So we know that this is the basic idea of radiation pressure. So pressure is like force per unit area. But how does something give you a force when it doesn't have mass? That's a question I want to pose to all of you. Think about this. We have like F equals ma, okay? But that's not going to work here because light doesn't have any mass. So how do we get pressure? How do we have light exerting a force or a pressure if it doesn't have any mass? Does it obey Newton's laws? Well, are Newton's laws completely incompatible with Maxwell's equations? Do Maxwell's equations just belong to a different part of the universe and the two theories don't coincide with each other? That would be sort of like what we have with gravitation and quantum mechanics today, where we have two different systems describing different aspects of nature and they don't seem to agree with each other. So this is kind of an interesting situation because I told you that the light has no mass, but yet it exerts a force because it's a pressure, force per unit area. So how does it do that? It does it because, remember, force is also equal to dp by dt, the rate of change of momentum with respect to time. And although light is massless, light does have a velocity, and it does carry momentum. And so that's why we can have radiation pressure associated with light, because light has momentum. So it can be shown that electromagnetic waves carry momentum p with a corresponding momentum density per unit volume of magnitude, dp by dv. That's just equal to E times B over mu naught divided by c squared. So the pointing vector S divided by c squared is the momentum per unit volume. That's an interesting relationship there. So then this momentum is a property of the field. It's not associated with the mass of a moving particle in the usual sense. Okay, so we can't really say that it's just like kinetic energy. So there's a little bit of a hand waving going on here because we're saying, well, it's got momentum. Don't worry about it too much, how it got that momentum. It's just a property of the field. The field itself has momentum. That turns out to actually not be too wrong, though, interestingly enough, because what turns out to be the case is, at the most fundamental level, even fields, quantum fields that haven't even formed into particles, we're just talking about fundamental fields here in the vacuum, those fields still have spin directions associated with them, which is a form of angular momentum. So it's not really so unreasonable to say that this light has some momentum associated with its intrinsic field that describes it itself. It's actually pretty accurate. So we can go with that. And that's what, classically, it works just fine. So then the Poynting vector magnitude is given by the flow rate of the electromagnetic momentum. It's the momentum transferred per unit time, per surface area per unit time. So we're talking about a momentum that's transferred. So the light is carrying momentum, it's striking a surface of some sort, and it's giving up its momentum to the surface in this process through absorption. The light is being absorbed by the surface, and that momentum transfer corresponds to a force. Radiation pressure. So here we have it. So we have dP by dt, 1 over the area of dP by dt. Notice we're writing it as a force here, just like I have over there. That's where that dP by dt comes from. And then that's going to be S over c. That's EB over mu naught c, speed of light in a vacuum. Okay, so we obtain the average rate of momentum transfer per unit area by replacing S by S average equals I. This momentum is responsible for radiation pressure. When an electromagnetic wave is completely absorbed by a surface, the wave's momentum is also transferred to the surface. Let's see how we're doing for time. Okay, perfect. So for simplicity, we'll consider a surface perpendicular to the propagation of direction. So we'll assume total absorption. Total absorption, that's what that means. So then using these ideas that the rate dP by dt at which momentum is transferred equals the force on the surface, which again comes from Newton's law reasoning, which they didn't say here, but I showed that there on the board. The average force per unit area due to the wave or radiation pressure is the average value of dP by dt divided by the absorbing area. So we use the subscript rad to distinguish pressure from momentum, for which the symbol P is also used. And then the radiation pressure then is just S average divided by C, or the intensity divided by C. So the radiation pressure, in terms of the Poynting vector magnitude, the average value of the Poynting vector, S average divided by C, it's also equal to the intensity divided by C. Okay, if the wave is totally reflected, the momentum change is twice as great. So a reflection is even better. We get even more, because then we have a double change in the momentum. And so then we have 2 times the S average divided by C is equal to 2 times the intensity divided by C. So for example, the value of I, or S average for direct sunlight, before it passes through the Earth's atmosphere is 1.4 kilowatts per meter squared. The average pressure on a completely absorbing surface then is 4.7 times 10 to the minus 6 pascals. Same units as pressure for like atmospheric pressure. So we can describe the radiation pressure in the same terms, but notice it's a lot smaller. So we don't, when we go out into the sunlight every day, we don't feel that pressure. We just feel the heat from it. But there is a pressure associated with it. And then the average pressure on a reflecting surface is twice this. So if we have a mirror, the mirror has twice this pressure, 2 times the intensity over C. These are very small, but they can be measured with sensitive instruments, so this has been demonstrated to be true. And the radiation pressure of sunlight is much greater inside the sun than at the Earth. Inside stars, there's so much radiation pressure that it changes the gas pressure within the star and helps prevent the star from collapsing under its own gravity. So when this fusion is occurring and we're generating massive amounts of light, the radiation pressure from within the sun, if I've got my sun here represented and it's like just got this corona and gas around it, there's all this radiation pressure from the internal structure of the star pushing outwards, helping to prevent the star from collapsing further under its mutual gravity. And what that really does is it helps, not only does it help prevent collapse, but it helps slow down the fusion rate. It helps to kind of prevent that a little bit in different ways. So the radiation pressure for stars can have dramatic effects on the material surrounding them as well. It changes the gas pressure as well. Because there's also, remember, there's also hydrogen and helium gas. It's ionized, but it's still gas inside of this star. It's hot gas under intense pressure. Perfect for fusion. So here we go. We've got this interstellar gas cloud. Now this is a slightly different situation. So in astrophysics, radiation pressure does all kinds of interesting things to dust particles. Because dust particles are tiny, so gas and dust that's floating out there in space, it gets moved around and shifted by radiation pressure. So you'll have this beautiful image of like a group of stars nearby a gas nebula, a cloud of gas, and the radiation pressure you'll see the gas actually moved by the radiation pressure from the star. Like it'll be like the gas will have a big chunk moved out of it where the radiation pressure has disturbed it. You can kind of see that here. So at the center of this interstellar gas cloud, a group of intensely luminous stars that exert tremendous radiation pressure on their surroundings, aided by a solar wind of particles. So the wind is sort of like you've got these ionized particles like nuclei, like hydrogen and helium nuclei. They're extremely fast moving particles that have been ejected from the star during stellar processes. This forms a solar wind. This is also the stuff that turns into the aurora borealis because we have a magnetic field around Earth that redirects these solar wind particles that the sun spits out at us away from us towards the pole, towards the North Pole and the South Pole. We have 2 different aurora there. That's what that is. The solar wind also comes about through here from the stars. And then over the past million years, the radiation pressure has carved out a bubble within the cloud 70 light years across. So we have this amazing carving out of this cloud by this radiation pressure. Okay, and then we've got an Earth orbiting satellite has solar energy collecting panels with a total area of this. If the sun's radiation is perpendicular to the panels and is completely absorbed, find the average power absorbed and the average radiation pressure force. Okay, so let's take a 5-minute break, and then we'll work this one when we get back. Because we're at 10:52. Yeah, a 5-minute break really quick. Okay, I think we'll go ahead and finish up this problem. So we've got this Earth orbiting satellite that has solar energy collecting panels, and its total area is 4 meters squared. So we can see these solar panels here. If the sun's radiation is perpendicular to the panels so that it can fully transfer its momentum to the panels, find the average solar power absorbed and the average radiation pressure force. So just to think about this one more time, because I know we talked about how, so first of all, a couple people asked a couple great questions. When I was talking about the solar wind, people said, well, you said that the solar wind was massless, right? Because light is massless. So solar wind refers to things emitted by the sun that are not light. So the solar wind is massive particles, because helium nuclei and these protons and things that fly out from the sun that we call solar wind, those are massive particles. So I want to differentiate that from radiation. So those two things are different. So that's a little like fine detail about that example that I talked about. And then in terms of the momentum carried, what is the momentum of light? Because this is actually going to be a nice segue into what we're going to do next. So when you think about our momentum, we're massive objects. What possible range of momentums can we have? Anything. We could have zero momentum if we're not moving at all. We can have, assumably, as high of a momentum as we want. We can just keep raising our velocity. We can never reach the speed of light, but as we increase our velocity tiny amounts, we're going to increase our momentum correspondingly. So then the question is, what is this momentum like for light? Well, the momentum is intrinsic to the light, and it stays constant for the light from the creation of the photon until it gets absorbed or whatever. So these light waves, they don't have a continuous range of momentums. They have one set momentum that's basically given by its frequency that's created when the light itself is created. So the momentum, and there's a little bit of a caveat there, because light, it turns out light can be shifted gravitationally, and so gravitational redshift can change the frequency of the light so that it does kind of have a continuous range of momentum, but not really, not in the same sense as like a massive object. So that kind of ties in with relativity, because in a reference frame, right, the speed of light is always constant. So that's like we have this constant speed of light, but then other objects can have different varying speeds. Maybe there's a connection there between these differing types of momentum. We won't have a whole lot of time to talk about energy and momentum and special relativity, but these kinds of observations about light being fundamentally different, you can bet that this is exactly what Einstein was thinking about when he was working on these theories and trying to make special relativity, or trying to make the laws of electrodynamics consistent in ways and fix these problems of relative velocities, which we're going to start talking about today. Anyway, so for this example, think of the light, the radiation pressure, as kind of like a bullet. Because what happens is the radiation pressure, even though radiation, the momentum that the radiation carries is of the way it gets its momentum is completely different than the way a massive object gets its momentum. The momentum for light just comes about. It just is given to it the moment the light is created. However, that momentum can still be shared with an object that does have mass, like a person or this satellite. Think of the light as a tiny bullet that strikes the area and transfers its momentum. The way you'd have like a stationary object, you fire a bullet, the momentum goes into the object and transfers momentum to that object. It's the same kind of process going on here with radiation pressure. It's a transfer of momentum from the radiation to the object, in this case, the solar panels. So, to solve this, we have to use the relationships of intensity, power, radiation pressure, and force. And before we used the intensity, which is the average power per unit area of sunlight, to find the radiation pressure of sunlight on a completely absorbing surface. So these values are for points above the atmosphere, which is where the satellite orbits. So we can take these values, and then multiplying each by the area of the solar panel gives the average power absorbed and the net radiation force on the panels. So we have the intensity is given to us as 1.4 times 10 to the third watts per meter squared. So then, although the light from the sun is not a simple sinusoidal wave, we can still use the relationships we found for power, intensity, and area for any type of light. it's valid for these as well. The sinusoidal version of it is just the simplest possible case. But remember, actually maybe you haven't had Fourier theory. Have you guys learned about Fourier series and things like that? Okay, so never mind. I can't really make that point for this class. But anyway, the basic gist of it is, if you can describe something as a sinusoidal function, if it takes other shapes, you can also describe those other shapes as like collections of sinusoids. So describing something that oscillates as its simplest case gives you the complete description. You just have to take different linear combinations to get whatever other situation you're talking about in the future. But we don't have time to talk about why that is. The reason why is the Fourier series, though. Okay, anyway, so we've got power and intensity times the area. So we have intensity given to us times the area, super simple. So it's 5.6 kilowatts of power. So then the radiation pressure, that's what we really want to know. It's 4.7 times 10 to the 6 pascals, which we didn't solve that in this problem. They did that in the earlier problem. They calculated it, and it was just given. So we know that. So then we know the total force is the pressure times the area. So the force is pressure times area. That's 4.7 times 10 to the minus 6th times the area of 4 meters squared. So that's 1.9 times 10 to the minus 5th newtons. So tiny. 1 newton of force is like you can barely feel it. This is like 10 to the minus 5 newtons. So it's absolutely tiny. Tiny, tiny, tiny. But anyway, that's the amount of force that the radiation pressure is given. Okay, that concludes this chapter on optics. So now we have to go into, so there's that's done. Now we have to start our special relativity chapter. This will be the remainder of the course. It's the coolest chapter in the book, and I made sure that we got to cover it. So, in 1905, we all know the famous Albert Einstein was working in a patent office, and he had his miracle year, and he published 4 amazing papers. Some of them they're all super famous. The Brownian motion is probably like the least famous one, but that's still also an important paper. And a lot of people don't know this, but Einstein did not just make contributions to physics in terms of special and general relativity. He also made contributions in statistical mechanics. In fact, like a lot of his time was spent working in statistical mechanics. So while he was doing this, he was also doing stuff with like Brownian motion. And the Brownian motion paper was important because, believe it or not, this is how far physics has advanced. In his time, it was still debatable whether or not atoms existed. And the problem is that there were some really good physicists like Ernst Mach and others who said atoms don't exist. It's fake. It's make-believe. Why these good, talented physicists came up to this conclusion and couldn't accept Ludwig Boltzmann's ideas about molecules and atoms, who knows? But it's really unfortunate because it basically created this big debate about whether or not atoms existed, and they couldn't decide. And then in the process, one of the guys that came up with the idea, Ludwig Boltzmann, he kind of committed suicide because he was so upset about the scientific debate and stuff. He felt like he was being completely discredited. So it created this really bad situation. And what happened was Einstein read Boltzmann's papers. And Boltzmann today is regarded as like one of the greatest of all times of physics. He's one of the goats. Like, he's up there. Okay? So, but in those days, he was a controversial figure. Well, Einstein said, what about this Brownian motion? When we see pollen molecules, they're bouncing around in all these random directions. What he was able to show mathematically with his calculations is that the only way this could occur is if there were molecules, fundamental building blocks, transmitting energy and kind of bouncing things around, kind of like the radiation pressure we just talked about, except not with light. Momentum transfer going on with tiny particles affecting the pollen grains. So that was the Brownian motion paper that he also published. That was a big deal too, because in that time the validity of the atomic hypothesis was debated. We didn't have the periodic table like we do today. That came later with quantum mechanics. They had elements, but they did not have this big, beautiful periodic table with all of the elements in the right order. Some of the elements were in the right order, but some of them were way off. And that came from proving that everything was, that molecules and atoms existed, that we did have fundamental building blocks called atoms. But anyway, Einstein did that with the Brownian motion. He started with that little thought experiment and basically said, hey, if these pollen grains are moving like this, the only way is if the molecules are striking them. Anyway, for special relativity, what he did was he took this idea of invariance. He said, okay, the laws of physics should be the same in any inertial reference frame. What does that mean by inertial reference frame? What it means is, it means a reference frame that's not accelerating. Are we in an inertial reference frame right now? No, we're not. The Earth is accelerating because it's orbiting the sun, and an orbit is a type of acceleration. However, because of the scale of things, because of how things have scaled, and also because of how we're just used to it, we don't notice this acceleration. So what happens in our non-inertial reference frame is when we do something like we fire a rocket, the rocket doesn't just go in a straight line. It curves off with some force. And there's this effect. It's called like the Coriolis effect. There's fictitious forces that get introduced. So we can do physics in non-inertial reference frames. Like when you're spinning around on a merry-go-round, if you try to do the same physics experiment that you do when you're not spinning, you're not going to get the same result. F equals ma has to be changed when you're accelerating. So, key point here, inertial reference frame means non-accelerating. It can be an object that's moving at a velocity, but it has to be moving at a constant velocity. The velocity is not changing, the direction is not changing. That's inertial. Okay, I'm really glad that I made that point, because that's something that isn't made to in a lot of classes what that clear explanation is, but that's what it is. Okay, so here's the first postulate that Einstein says. The laws of physics are the same in every inertial frame of reference. If the laws differed, that difference could distinguish one inertial reference frame from the others or make one frame more correct than the other, which is no good, because that's nonsense. We have to have the laws of physics being universal. We can't have one observer is right and the other observer is wrong. If that's true, then our theory is wrong. So as an example, suppose you watch two children playing catch with a ball while the three of you are aboard a train moving with constant velocity. Okay, so this is going to be, I wish I had a video for this actually. When I do this again, I might need to find a video of this. Let's say you observe the motion of the ball. No matter how carefully done, you can't tell how fast or whether the train is moving. And this is because the Newton's laws of motion are the same in every reference frame. Okay, so what the heck did they just say there? What they said was, two children are playing catch with the ball while we're aboard a train moving with constant velocity. Your observations of the motion of the ball can't tell you how fast or whether the train is moving. Okay, so it's pretty simple. So imagine you're standing on a train and it's moving with constant velocity and there's no friction. You can't tell if the train is moving or not because it's just the same as if it wasn't moving at all. So if I'm moving with constant velocity, I can always transform to a frame where I'm not moving at all. But if the kids were playing catch with the ball and the train started accelerating, the physics would change and a lot of things would change from that situation, and then we could tell that there was something going on. So the laws of physics change in frames of reference that accelerate, but they do not change in frames of reference that are moving at constant velocities. And that's the picture we're thinking of. You know how when a train accelerates, the laws of physics have to be modified because whatever you're doing, it jolts you, it introduces other things into the dynamics of the situation. Okay, let's see. Okay, so why is this like this? Okay, let's read this. So another example is the electromotive force. Remember that, the EMF in Faraday's law? We have it induced in a coil by a nearby moving permanent magnet. In the frame of reference in which the coil is stationary, the moving magnet causes a change in the magnetic flux. Okay, good. Just checking my battery here. Through the coil. So we have a moving magnet that causes a change in flux through the coil, and it induces an EMF. But in a different frame of reference in which the magnet is stationary, the motion of the coil through a magnetic field induces the EMF. So according to the principle of relativity, both of these frames of reference are equally valid. Hence, the same EMF must be induced in both situations, shown. So we've got this same EMF here. Sorry. Here's a better picture of it. Okay, so the magnet moves with some velocity this way, and we produce an EMF. So remember, we have a changing magnetic field. The south pole is going towards the coils of the magnet. That produces an EMF. But if we leave the magnet stationary and we move it up this way with this velocity, it should be the same, and it is. So we've got the coil. If I've got the magnet going this way, the change in flux should be the same as if I take the magnet, hold it stationary, and move the coil. That's the point they're illustrating. Does that make sense? Yes. Okay, so we say that this Faraday's law obeys the principle of relativity. Because if Faraday's law gave us a different result, if one thing was moving versus the other, then Faraday's law would be assigning some kind of special property to the magnet and the coil and saying these two are intrinsically different somehow, and that would be inconsistent with a universal law. But since they obey relativity, we have a very powerful universal law here. So that was Einstein's starting point, was look at these Maxwell's equations. They're invariant. That's great. Okay, so Faraday's law is consistent with relativity. And all the laws of electromagnetism are the same in every inertial frame of reference. Equally significant is the prediction of the speed of electromagnetic radiation derived from Maxwell's equations. According to this analysis, light and all other electromagnetic waves travel in vacuum with a constant speed, now defined to be 2.9 times 10 to the 8th. So we'll see that the speed of light plays a big role in this. Okay, so that was his first postulate, the principle of relativity. Laws of physics should be the same in every inertial reference frame. Second postulate has to do with light. This was a big jump. This is kind of like next level thinking. So the 19th century, physicists thought that light traveled through this stuff like an ether. Why would they think that light travels through an ether? Well, it's not all that different from like a Higgs field, if you think about it. Nowadays, physicists believe that there's a field propagating since the Big Bang that's been, that basically allows particles like leptons to gain mass. It's not the only source of how things get mass, but it does, in theory, in the standard model, it's how leptons get their mass. Anyway, back then, they believed that there was like this field called the ether. And I'm not saying that the Higgs field is fake either. There's some people who do say that, but I'm just saying this idea of there being a universal field is still around in physics in different forms today. In their day, they had it associated with light. And they said, well, you know, you've got this nice little ripple in a pond, but what's the ripple actually caused by? Well, it's caused by the water itself. So the ether was supposed to be this stuff that was allowing the light to ripple. And Einstein just says, nope, not needed. Light is different. Light has this other nature. Now, why is that true? Why does light not need a medium to propagate? It's because of quantum mechanics. because they didn't know this at the time, and Einstein didn't really know it either. But everything is a wave/particle duality, including light and including objects with mass, including like electrons and things. It's because the fundamental building blocks of nature are fields, and what we see with this macroscopic world is trillions upon trillions of field interactions that give us the world that we see. But at the fundamental level, it's a field. And light, because it's a field, it behaves this way. It doesn't need a medium to propagate because it's an electromagnetic field. So that was his postulate. And they did this experiment, Michelson and Morley, and they did it, I think, in California, where they looked at if there was an ether, there should be a way to measure the motion of the Earth relative to the ether. So they measured it, and they found nothing, no change. So that added fuel to the hypothesis that Einstein had about light not needing an ether to propagate. So his conceptual leap, where he got it from, was recognizing that if Maxwell's equations are valid in all inertial frames, then the speed of light in a vacuum should also be the same in all frames and in all directions. So he used Maxwell's equations. He didn't just come up with this out of magic, out of thin air. He started from a very reasonable, common sense hypothesis about the laws of physics being valid in every reference frame. And then he said, well, he found a clever connection through Maxwell's equations, because remember, Maxwell's equations have the speed of light everywhere in them. They're all over the place. So he spent all this time, all these days and years, a couple years, looking through all these equations and saw, hey, in order for these equations to actually be true, this can like never change. If this changes, all that we see is incorrect. So when people would do these like experiments, they would do experiments and they would say, hey, this scientist in some country, he found that the speed of light is not constant. Are you worried about this? And he'd laugh and say, no, I'm not worried at all. He was completely confident, because it's like if this wasn't the case, then none of these laws would have been discovered to begin with. It's like seeing the forest through the trees. It's like a big, giant thing that's staring right at you, but it's so hard to see it until you do see it. It's like genius is hitting a target that nobody else can see, right? That's the famous philosophical quote about it. So that's the big second postulate. So two observers measure the speed of light in a vacuum. One is at rest with respect to the light source, and the other is moving away from it. Both are in inertial frames of reference. According to the principle of relativity, the two observers must obtain the same result, despite the fact that one is moving with respect to the other. So let's consider this situation here. Sorry, let me go back. So we've got this spacecraft, and it's moving at 1,000 meters per second, and it fires a missile straight ahead with a speed of 2,000 meters per second. So it's already going at 1,000. The velocity addition rule of Galileo worked with relativity as well. He's the one who figured out, hey, if you've got a car moving this way at 100 and a car moving this way at 100, when the two collide, it's like they strike each other at 200 miles per hour. And that's why you have like such a catastrophic collision in a head-on collision. That's the same idea here. This thing's already moving at 1,000 meters per second, and then it fires a rocket even faster, so the speed of the rocket should be 2,000 plus 1,000 meters per second. But as we'll see, taking the speed of light as a constant, we're going to have to modify that. That's not going to hold valid in the physical universe. It's only valid at low speeds. As we get to higher speeds, you'll see that this velocity addition formula, this Galileo velocity addition formula, is not valid. But let's get there. So, according to Newtonian mechanics and Galilean relativity, It's 3,000 meters per second. But now suppose the spacecraft turns on a searchlight pointing in the same direction, and the observer on the spacecraft measures the speed of light emitted by the searchlight and obtains the value of c. According to Einstein's second postulate, the motion of the light after it left the source cannot depend on the motion of the source. So the observer on Earth who measures the speed of this light must also obtain the value of c, not c plus 1,000 meters per second. In other words, this thing turns on a light and sends out a signal. The light source is traveling at 1,000 meters per second, but the light wave from the source cannot be going 1,000 plus c. So unlike the rocket here that was sent out and the velocity was added to it, the light can't do that. And that's the contradiction. So light doesn't obey. If we say light is in the same speed no matter what, this velocity addition formula doesn't work. So how do we fix this? The result contradicts our notion of relative velocities, and it may not appear to agree with common sense. But again, we have to respect Maxwell's equations. If we say, hey, these equations for electrodynamics are always true, they've been tested in the laboratory, then we better play around with this situation a little more and figure out what's going on here. So, Newtonian mechanics makes correct predictions about relatively slow moving objects, like missiles and objects firing missiles. But when something's going the speed of light, it's wrong. So how do we fix this? Newtonian mechanics tells us incorrectly that the light should move at a speed greater than c relative to the observer on Earth. So that would violate Einstein's second postulate. So the postulate then is that c in a vacuum is the ultimate speed limit. It's impossible for an inertial observer to travel at c, the speed of light in a vacuum. And when they say inertial observer, they mean an inertial observer who has mass. Okay, because all of us that do have brains, we do have mass. So light is also could be an inertial reference frame, but it moves fast. It moves at the speed of light. But anything else that's not light has to move slower than c. Okay, we can prove this by showing that at c, moving at c implies a logical contradiction. Suppose the spacecraft S prime in this figure is moving at the speed of light relative to the observer on Earth, so that Vs prime slash S is equal to c. Okay, so assume it's moving at the speed of light. If the spacecraft turns on a headlight, the second postulate now asserts that the Earth observer measures the headlight beam to be also moving at c. Thus, this observer measures the headlight beam and the spacecraft move together, and they're always in the same point in space. But Einstein's postulate also asserts that the headlight beam moves at speed c relative to the spacecraft, so they cannot be at the same point in space. Okay, so this is really weird. So now we're saying, okay, the spacecraft's moving at the speed of light, okay, and then it turns on a light beam. If the spacecraft was moving at the speed of light and the light beam can only travel at the speed of light, then the spacecraft and the light beam never travel away from each other. But that's not true. In the frame of reference of the spacecraft, when it turns on its light, it has to still see the light moving away at it at the speed of light. So what that means is, number one, the spacecraft cannot move at the speed of light, because then if it could, then they would always be at the same point in space, and they can't, because when I'm on the spacecraft moving at constant velocity, when I turn on the light, in my frame of reference, the light has to move away from me at the speed of light. So first of all, it means that. And second of all, if this spacecraft is going really, really fast, then we have something really weird going on here. Because then, if I'm in the spacecraft, I have a situation where I'm not making the same observation as, in every respect, as a person who's not in the spacecraft. I can't be, right? The only thing that me and somebody not in the spacecraft can agree on is that light bulb that I turned on is going at the speed of light. That's it. Everything else is going to be different. the lengths of things, the time passage of things, all those things are going to be modified. Okay, so this contradictory result of the light and the thing, yes? You would still, if you're going just below the speed of light and you turn on the light bulb, you would still see it moving away at the speed of light. Yes. So I know that's weird. That's why all of this other stuff has to change in order to make that true. So it's not an easy fix. It's got some stages to it. Okay, so to start with, great question, by the way. That's what I was trying to get you to think about, how weird that is. So this contradictory result can be avoided only if it's impossible for an inertial observer to move at c. So that fixes our first problem. We say, okay, if you've got mass, you can't move at the speed of light. Then you can say, what would I see if I were traveling at the speed of light? And then the question's basic flaw is that you cannot travel at the speed of light. So I actually disagree with that point that book makes. I think the book misunderstood history. Einstein actually imagined moving at the speed of light for a different reason, but he never assumed that you could move at the speed of light. I don't know, that sentence is incorrect. Okay, but that's fine. Okay, so Galilean coordinate transformations. Let's restate this argument symbolically. Okay, so first we're going to go through and we're going to actually derive the velocity addition formula that's correct, that everybody can agree on. But to start with, we have to start with the good old-fashioned Galilean coordinate transformation, which is just like normal relative velocities adding. If I'm going 100 miles per hour and if I'm on a train platform that's going 100 kilometers per hour and I start running at 3 kilometers per hour, how fast am I going? 103. That's the normal velocity addition formula of Galilean coordinate transformations. Okay, so that's what we have here. So we've got this frame S prime. It moves relative to frame S with constant velocity u along the common x prime axis. Okay, so we've got this origin here. We've got this distance x, and then we've got this second coordinate system that's moving away. So you can think of it as there's two origins, O and O prime. Each of these coordinate sets corresponds to a different observer. O and O prime coincide at time t equals 0. So this must be after some time has elapsed, some time t. And this coordinate has traveled a distance vt, where v is given by u here. U means the relative velocity difference. So if this thing is going 5 meters per second and this thing is stationary, it's traveled 5 meters in 5 seconds. Make sense? Yeah. Okay. So we've got this x is equal to x prime plus vt. Okay. So let me erase this and let's put this out on the board really quick because it's important. So we've got x equals x prime plus ut. And what do I mean by x? This is x. Let me make this bigger. Okay, so we've got this x here, and then this other axis, x prime. And it's traveled some relative distance ut. Because remember, the relative velocity, if this thing's going, they start at the same point, and then we start the clocks. This one starts moving. It's separated by this. So this describes how the 2 points are equal. So x is equal to x prime plus ut. At time t equals 0, x just equals x prime. So that's where that comes from. And then we're only considering a change in the x direction, so y and z are always the same. Y equals y prime, and z equals z prime, because these other dimensions, they're not changing. They're just always lined up. We only have motion along the x. Make sense there? Okay, great. That's the Galilean coordinate transformation. Simple. So, these equations, based on the familiar Newtonian notions of space and time, are the Galilean coordinate transformations. If particle p moves in the x direction, its instantaneous velocity, as measured by an observer stationary in s, is vx equals dx by dt. Remember that from classic physics. And so then its velocity is this. Okay, so we can derive a relationship between vx and vx prime by taking the derivative with respect to t. So we take a derivative of this, and we get that d by dt, take d by dt of this, and then we get dx by dt equals dx prime by dt plus u, because d by dt of ut is just u. Everybody see how I got that? Okay, because that technically is a differential equation. Could be a little bit new to you. All right. Now, dx by dt is the velocity vx measured in s. So this is the velocity that we measure in our s frame. And dx prime by dt is the velocity measured in s prime. So we get the Galilean velocity transformation for one-dimensional motion. So vx, this is just calling this vx equals vx prime plus u. So now we have our velocity transformation by just taking the time derivative of the coordinate transformation. Now, here's the fundamental problem. Applied to the speed of light in a vacuum, this equation says that c is equal to c prime plus u. c equals c prime plus u, which we know is wrong. So this is not going to work. We're going to have to fix this and make it work for the speed of light. So the resolution involves some modifications. The first idea to be changed is the assumption that the observers in frames s and s prime use the same time scale, formally stated as t equals t prime. So t, in this, by assumption, implicitly, t equals t prime. But in our new system, t is not equal to t prime. So the observers will have a different sense of time passage. That's the key. So we're going to have to define the velocity in frame s as v prime equals dx prime dt prime, not as dx prime dt. So we're going to have to add a prime to this one, because t prime is different from t. So I added a little prime to that. Okay. This may seem contrary to common sense. And I'm going to double check the time here. We have enough time to do this, actually. To illustrate this point, here's a version of one of Einstein's thought experiments. Okay, so we have this train, and it's moving with a speed comparable to the speed of light with uniform velocity. Two lightning bolts, bang, they strike. They strike a passenger car, one near each end. The bolt leaves a mark on the car and one on the ground at the instant the bolt hits. The points on the ground are labeled A and B in the figure. Okay, so you see these 2 points here, A and B, are both struck at the same time. Stanley's at a stationary point. He's observer S. He's on the ground. Mavis is going to be S prime. So S and S prime. These two velocities correspond to these two different observers. This is going to be Stanley, and this is going to be Mavis's velocity. Okay, so the lightning strikes, and Stanley is stationary midway between A and B. Okay, Mavis is moving with the train at O prime in the middle of the passenger car, midway between A prime and B prime. Both Stanley and Mavis see light flashes emitted from the points where the lightning strikes. The lightning hits the front and back of the train and hits the ground at points A and B. So it hits the front and back of the train. So there's 4 strikes here. It strikes the front and back of the train at A prime and B prime, and the ground at the same point A and B in front of it. There's a picture of that. Okay. Suppose the 2 wave fronts from the lightning strikes reach Stanley at O simultaneously. He knows that he's in the same distance B and A, so Stanley concludes that the 2 bolts struck B and A simultaneously. He sees the light flashes hit A and B at the same time at this point, by definition. Mavis agrees that the 2 fronts reached Stanley at the same time, but she disagrees that the flashes were emitted simultaneously. What? So he sees the light hit at the same time, and she doesn't. How is that possible? Well, Stanley and Mavis agree that the 2 wave fronts do not reach Mavis at the same time. Mavis at O prime is moving to the right with the train. Okay, so we need to take this image back here, and I need to put it in here so we can refer to this. Okay, so Mavis is moving this way with the train. Okay, so she's going like this. She's moving this way with the train. So she runs into the wavefront from B before the wavefront from A catches up to her. So the wave is going like this, and it's going like this. This is hard to see, but it's going like this. She's gonna hit the wavefront at A or B before at A prime catches up with her. Okay? Because she's going this way. And the wavefront is coming like this. So from her vantage point, because she's got this relative velocity with respect to the light, she sees the front B hit at a different time. She sees it from B prime before at A prime. However, because she's in the middle of the car, equal distances, her observation is that both wavefronts took the same time to reach her because both moved the same distance at the same speed, c. So she concludes that the lightning bolt at B prime struck before the one at A prime. Stanley at O measures the two events to be simultaneous, but Mavis at O prime does not. So whether or not two events at different x locations are simultaneous depends on the state of motion of the observer. And so that's really weird to think about. So you may want to argue that the lightning bolts are simultaneous and that if Mavis at O prime could communicate with the distant points without the time delay caused by the finite speed of light, she would realize this. But that would be erroneous. The finite speed of information transmission is not the real issue. If O prime is midway between A prime and B prime, then in her frame of reference, the time for a signal to travel from A to O prime is the same as that from B prime to O prime. So two signals arrive simultaneously at O prime only if they were emitted simultaneously at A prime and B prime. Okay, so in other words, what matters is the person's reference frame. In Stanley's, the reference frame in which the light emission is simultaneous is in his reference frame because he's the one standing stationary on the ground, and for him, the light is emitted at the same time and strikes the car at the same point. He's the stationary reference frame. In order for her to see that, she would have to be in a stationary reference frame, not a moving one. But she is in a moving reference frame. So she doesn't see this process occurring as a simultaneous event. She sees one thing happening before the other. So, two signals arrive simultaneously at O prime only if they were emitted simultaneously at A prime and B prime. In this example, they do not arrive simultaneously at O prime, And so Mavis must conclude the events at A prime and B prime were not simultaneously, even though they were simultaneously happening for Stanley. Furthermore, there's no basis for saying Stanley or Mavis is right or wrong. No inertial frame of reference is more correct than the other. It's just that each observer is correct in their own frame of reference. So when this physical process of nature happens, this simultaneity, it's not intrinsic. That's really hard to wrap your head around. You'd think that if some process occurs, it occurs the same for everybody and at the same time, but that's not true. It turns out that for different observers in different points at relative velocities, or at different points even in gravitational fields, which we're not going to get to because that's general relativity, but just know that that's the case. For either of those, the time is relative. It's not absolute. So whether two events are simultaneous depends on the frame of reference. Simultaneity plays an essential role in measuring time intervals. So it follows then that the time interval between two events may be different in different frames of reference, as they are in this example. So we have to figure out how to compare these time intervals in different frames of reference. And we can actually derive a quantitative relationship between time intervals in different coordinate systems. And we're going to do that. But I think we should probably wait until next week because we're in the last couple minutes, and I'd have to repeat this slide anyway to build on it for the next class. So we'll call it today, and I'll see you all Thursday.